There is a place not far from here in cosmic terms where the laws of physics simply stop working. Not bend, not stretch, stop. Mathematics that has described every star, every atom, every fraction of a second since the Big Bang walks up to its edge and falls silent. In the next few minutes, we're going to walk to that edge together. We'll see why Einstein's greatest theory predicts its own destruction inside a black hole. We'll meet a paradox that nearly tore physics apart for 40 years. And we'll end with the unsettling possibility, taken seriously by some of the best minds alive, that black holes may be telling us the universe itself is not what it appears to be. In November 1915, Albert Einstein finished a set of 10 coupled equations, now known as general relativity. They describe gravity not as a force, but as the curvature of spacetime itself. Mass tells space how to bend. Bent space tells mass how to move. Within months, the equations had explained the strange wobble in Mercury's orbit that had baffled astronomers for decades. Just weeks later, on the Russian front of the First World War, a German physicist named Karl Schwarzschild, sick, exhausted, serving in the artillery, found the first exact solution to Einstein's equations. He sent it back to Einstein by post. Einstein was astonished. But buried inside Schwarzschild's beautiful solution was something deeply uncomfortable. At a certain radius around any sufficiently compressed mass, the equations produced infinity. For decades, physicists assumed this infinity was a mathematical glitch, a trick of bad coordinates. Surely nothing in nature could actually behave this way. Einstein himself believed black holes were impossible. In 1939, he published a paper arguing they could never form in the real universe. He was wrong. In 1939, the same year Einstein dismissed them, Robert Oppenheimer and his student Hartland Snyder showed mathematically that a sufficiently massive star, at the end of its life, has no choice. Gravity wins. The core collapses past the point of no return, and nothing, not nuclear pressure, not the speed of light itself, can stop it. By the 1960s, real candidates were found in the sky. By 2019, the Event Horizon Telescope released the first direct image of one in the heart of galaxy M87. They are real. They are everywhere. The Milky Way alone may contain 100 million of them. But here is where the trouble begins. Because once you accept that black holes exist, you have to accept what general relativity says is inside them. And what general relativity says is this: at the very center of every black hole sits a singularity, a point of infinite density, infinite curvature, where space and time as we know them cease to exist. It is not a small object. It is not an object at all. It is a hole in the fabric of reality. Infinity is not a number. When a physical theory predicts infinity, it is the theory's way of telling you it has failed. It has been pushed past the domain where it works. Black holes don't just contain a problem for physics. They contain the place where our best theory of gravity admits it does not know what happens next. To understand why this matters so much, you need to know that modern physics rests on two pillars: general relativity, which governs the very large, galaxies, stars, the expansion of the cosmos, and quantum mechanics, which governs the very small, atoms, electrons, the flickering vacuum of empty space. Both are stunningly accurate. The standard model of particle physics has been verified to better than 1 part in a billion. General relativity correctly predicted gravitational waves, observed by LIGO in 2015, exactly a century after Einstein wrote them down. The problem is that the two theories are mathematically incompatible. Quantum mechanics treats space-time as a fixed stage on which particles dance. General relativity says spacetime is the dance. It bends, ripples, and stretches. For almost a century, attempts to merge them, to build a theory of quantum gravity, have failed. Under normal conditions, this doesn't matter. Gravity is so weak at atomic scales that you can safely ignore quantum effects in cosmology and ignore gravity in particle physics. But inside a black hole, both theories are screaming. Mass is enormous. Distances are vanishingly small. You cannot ignore either one, and they refuse to agree. In 1974, Stephen Hawking made the situation infinitely worse. He applied quantum field theory to the region just outside a black hole's event horizon and discovered something nobody expected. Black holes are not perfectly black. The intense curvature near the horizon causes pairs of virtual particles in the quantum vacuum to be torn apart. One falls in, one escapes. To a distant observer, the black hole appears to glow, faintly, thermally, like a dying ember. This is Hawking radiation, published in Nature in 1974, and it is one of the most influential predictions in modern physics. Hawking radiation means black holes evaporate, slowly. A stellar mass black hole takes longer than 10 to the 67th power years to vanish, vastly longer than the current age of the universe. But eventually, they disappear. And this is where the universe really breaks. Quantum mechanics has an iron rule. Information cannot be destroyed. If you burn a book in principle, the information about every word is still encoded in the smoke, the ash, the radiation. Run the laws of physics backward, and you should always be able to reconstruct the past. This principle, called unitarity, sits at the very foundation of quantum theory. Without it, probabilities don't add up to one. Without it, physics doesn't work. But Hawking's calculation showed that the radiation streaming out of a black hole is purely thermal, random. It carries no memory of what fell in. So when the black hole finally evaporates and disappears, all the information about everything it ever swallowed, every star, every planet, every photon, is gone, erased from reality. This is the black hole information paradox, and it has haunted theoretical physics for half a century. The paradox is not academic. Either general relativity is wrong about how black holes radiate, or quantum mechanics is wrong about information, or, and this is what most physicists now believe, both theories are approximations of something deeper, and that deeper theory is hiding inside the black hole. In 1997, the Argentinian physicist Juan Maldacena proposed something extraordinary. His paper, published in Advances in Theoretical and Mathematical Physics, has been cited over 20,000 times, one of the most influential papers in theoretical physics ever written. Maldacena showed that a universe with gravity inside it can be mathematically equivalent to a quantum theory without gravity living on its boundary. This is the holographic principle. It suggests, astonishingly, that all the information in a three-dimensional region of space, including a black hole, can be encoded on its two-dimensional surface. Reality may be a kind of projection. If Maldacena is right, and the consensus is steadily growing that he is, then black holes are not destroying information. They are scrambling it onto their event horizons, where it leaks out, slowly and subtly, in the Hawking radiation. In 2019, a team of physicists, led by Jeffrey Pennington and independently by Ahmed Almhairi, Netta Engelhardt, and Henry Maxfield, used a tool called the quantum extremal surface to derive a curve called the Page curve from the equations themselves. Strong evidence that information does in fact escape. Their work, published in the Journal of High Energy Physics, was hailed as a major breakthrough. The paradox may be cracking, but the cure is, in some ways, stranger than the disease. If the holographic principle is correct, the consequences extend far beyond black holes. Our entire universe, every galaxy, every atom in your body, this video you are watching, may be a holographic projection from information encoded on a distant boundary of space-time. Space itself may not be fundamental. It may emerge like temperature emerges from the motion of molecules, from a deeper layer of quantum entanglement. This is no longer fringe speculation. In 2010, the physicist Mark van Ramsdonk published a paper in General Relativity and Gravitation showing that if you remove the entanglement between two regions of a holographic universe, space-time itself tears apart. Space-time, in this view, is woven together by quantum entanglement. Black holes don't break the universe. They reveal what the universe actually is. There is no consensus yet. String theory, loop quantum gravity, causal set theory, different camps offer different answers. The Event Horizon Telescope, the LISA Gravitational Wave Observatory scheduled for the 2030s, and even tabletop experiments measuring tiny gravitational effects on quantum states are all closing in on the question. But the deeper truth, slowly emerging, is that the singularity at the heart of every black hole is not a failure of physics. It is a clue. It is the place where the disguise slips, where the smooth, comforting fabric of reality reveals the strange, computational, entangled machinery underneath. A black hole, in the end, is a window. A monstrous, beautiful, terrifying window into the actual nature of space, time, and information. We thought black holes broke the universe. They may instead be showing us what it has always really been. A century ago, Einstein wrote down equations that predicted their own end. A young soldier in a snowy trench solved them and saw the impossible. Hawking found that they glow. Maldacena found that they whisper. And a generation of physicists working today are finally beginning to listen. We do not yet know what lies at the center of a black hole. We may never travel there. But the mathematics, the radiation, the shadows captured by our telescopes, they are all telling us the same thing. The universe is deeper than we imagined, stranger, more elegant, more entangled. Reality, it seems, has a basement, and black holes are the staircase. If this glimpse into the edge of physics moved you, subscribe to Cosmic Edge and walk a little further into the dark with us.